Continuing on with our linear to rotational analogs, we're going to next look at the conservation of angular momentum. Remember, we conserved linear momentum in collisions or explosions because in the absence of external forces, the momentum can't change. Well, angular momentum is the rotational analog of linear momentum. If you remember linear momentum, we used a P to represent linear momentum. It's equal to the mass times the velocity. Well, let's look at the rotational analogs. The rotational analog of mass is moment of inertia. The rotational analog of velocity is angular velocity. So the angular momentum, which is represented by capital L, is equal to the moment of inertia times the angular velocity. Now, going back to our rotational analogs, net torque is the change in angular momentum with time, just like the net force, if you remember, was equal to the change in linear momentum with time. Right? So, if there is no net torque on the system, the angular momentum can't change with time. So it's conserved. Again, in the absence of a net torque, it is conserved. If it's conserved, that means the initial angular momentum must equal the final angular momentum. And again, your book it doesn't use the subscripts I and F, it uses just the letters and then the prime, meaning the after. I don't like that notation. I think it's a little more, this is the way of writing it's a little more explicit, but you can use whatever you're comfortable with. But just note that these are the same equations you have in your textbook. So if the initial angular momentum, right, the initial moment of inertia times the initial angular speed or velocity is equal to the final moment of inertia times the final angular speed. So in the absence of external torque, angular momentum is conserved. And we'll do a very short demo of that in a moment. Welcome back. So I have here two masses. Each mass is a 2 kilogram mass, so about 5 pounds, a little less than 5 pounds. I have two of them. And I'm sitting on a stool that has a very low frictional coefficient, so it spins very easily. So I can just put my feet up and spin around. So I've given myself rotational motion. I have angular speed. So I have angular momentum. I can change the amount of rotational speed that I have, right? So looking at that bottom equation again, the initial moment of inertia times the initial speed is equal to the final moment of inertia times the final speed, which just simply means that if I change my moment of inertia, my angular speed has to change as well. Otherwise, that equation doesn't work. So how am I going to change my moment of inertia? I'm going to give myself a very large moment of inertia by taking these masses and holding them out at arm's length. Make sure. All right, holding them out at arm's length. That gives me a very large I along the axis of rotation, right? My butt through my spine out through the top of my head, that's my axis of rotation on this chair. So the more mass I put away from that axis of rotation, the larger my moment of inertia, right? mr squared. So my r, the radius, is going to be the length of my arm, and the mass I'm putting out there is my arm, of course, my hand, but also these masses. So that's going to be my initial moment of inertia. And then as I start rotating, I'm going to pull these masses in towards the axis of rotation. When I do that, I change my I. I change my moment of inertia. Remember, moment of inertia is the mass distribution. I go for a very large mass distribution to a small one compared to the axis of rotation. So if IF is smaller than I sub I, right? If my final moment of inertia is smaller than my initial moment of inertia, then my speed, angular speed omega sub F, should be larger in order for that equation to balance. If one of the terms gets smaller, the other term has to get larger to compensate. So let's try that out. So I put this out. I'm going to spin around. Hopefully I don't hit anything. So I have some angular speed, right? Now I'm going to pull in these weights. I'm going around much faster. Now I put them back out. I slow down. put them back in, I move faster. That's conservation of angular momentum. And it's useful for, well, we have the Olympic Games right now. For those of you watching the recording after 2016, they're over. But if you've watched the Olympics, there are two big events that use conservation of angular momentum all the time. One is diving. When a diver jumps off the board, he or she is extended and they have a very slow rotation. When they tuck in, they'll spin more rapidly. So it allows them to complete more flips as they go through. And then before they go into the water, they extend again, so their rotation slows. Figure skaters are another example, although they do it in a different axis, right? Figure skaters will jump with their arms, start spinning with their arms wide, then pull in and rotate much more rapidly, and then extend their arms again. So conservation of angular momentum is, again, an important concept in physics. It's why when planets go around the sun in non-circular orbits, Earth actually travels a little bit faster when it's closer to the sun in January than it does when it's further from the sun in July. The difference is the fact that this conservation of angular momentum, so Earth is the same mass, so it's closer to the sun, I is a little bit smaller, so omega has to be a little bit bigger in order for momentum to be conserved. And Kepler's second law of planetary motion, with the equal areas swept out in equal times, that's a consequence of conservation of angular momentum. And that's how it was first measured by Kepler. Again, we're assuming orbits are circular for the most part, but they're not quite. So this is conservation of angular momentum, and there are problems worked out in your book as examples, and of course the problems that I've posted as examples. Listen to those, go through those if you get stuck, and then try to work on the problems for the homework. Post on the discussion board, of course, if you get stuck in any way.